Welcome to the next session, my dear friends. So in the previous session we have discussed about the chemical impurities. Now we are discussing biological impurities of water. Okay, biological impurities of water. See, biological impurities means the pathogens like bacteria, virus, protozoa, amoeba. So all these things are the biological impurities, so which are not visible to our naked eye directly, so which needs to be observed under microscope. Okay, so among all these microorganisms, the most important and most widely spreaded microorganism is bacteria. Okay, that is why generally we majorly use this biological impurities technique to take care of bacteria and also virus also, to some extent virus also. Now, because if you can find bacteria and virus, all other things can be taken care of. So if you, because the most critical microorganisms which are harmful is bacteria and virus. So biological characteristics. See, biological characteristics can be determined very easily. There are 4 methods, and again these 4 methods are subclassified as 2 methods. One is so qualitative and another one is quantitative methods. So there are 2 kinds of methods basically, that is qualitative method, qualitative, and another one is quantitative method. Qualitative method as well as quantitative method. So the term itself says qualitative means it only finds whether the bacteria or microorganisms are present or not. So it cannot explain you what is the concentration of it. It cannot estimate the concentration of it, but it can say whether the microorganism is present or not. Whereas if you go for quantitative, so in quantitative, so there will be a defined procedure by which we can identify or we can estimate the concentration of the microorganism also. So here only we can find whether the microorganisms are present or not. Here we can determine the microorganisms concentration also. Okay, this is a preliminary examination and this is a perfect identification of the microorganism. Okay, so in this also there are 2 methods. One is plate count test, and another one is membrane filter technique. Membrane filter technique. See, plate count test and membrane filter technique. See here, in plate count test, very simple, these tests are very simple to understand. See, whenever you take a microorganism or any kind of organism, so organism can grow only with food. When there is no food, no organism can grow. Even living beings like us are also grow only when we get a sufficient amount of food. So similarly here the microorganisms are also given the good amount of nutrients by which they can grow. So if they grow, so they will form colonies. If they grow, they will form colonies. These colonies can be easily observable in a microscope. Okay, so if a single microorganism is present, then it is difficult to understand the behavior of the microorganism. But if a group, if you are looking, then the group behavior can be easily observable. That is what we do here. So there will be a small conical plate. So there will be a small conical plate called Petra dish. So it is a Petra dish. So in this Petra dish, so we will take some raw water, which is in which you are assuming that microorganisms are present, and we will give some kind of nutrients here. So some kind of agar nutrient. So there are different kinds of nutrients are present for as a food of microorganism. So these nutrients name and all are not needed for the examination. So we will give some kind of nutrient and we will create suitable conditions also. Not only giving food, we need to keep the temperature which is sufficient for the organism's growth, that is 37 degrees temperature we need to provide for about 24 hours. Okay, we need to provide the temperature also for sufficient amount of duration for the growth of microorganisms. So once you give the nutrient, we give a proper temperature and proper duration you have given, then the growth of microorganism you can observe easily. So now in plate count test, on this plate how many colonies you are observing, that is nothing but plate count test. Okay, that is nothing but plate count test, but this will not give you the concentration, it will give you number of colonies present in the water, but exactly what is the concentration of microorganisms we cannot identify in this. Okay, so that is why this is a qualitative method. And membrane filter technique is also another qualitative method. In this you will be having a membrane, so filter paper. So membrane is nothing but filter paper. So membrane is nothing but a filter paper which can trap virus also, which can trap even virus also. Okay, so this is membrane. So on this membrane what we will do, we will allow the raw water to pass through this membrane. We will allow the raw water to pass through this membrane. So what happens? So whatever the virus, bacteria, whatever be the microorganism present in the water will get arrested on the top of this membrane. It will get trapped on the top of this membrane. Now on this top of the membrane also we will give some kind of nutrient like lactose broth. So we will give some kind of nutrient. So using this nutrient what happens? It will grow. So the microorganism will grow, and after 37 degrees, at 37 degrees temperature for about 24 hours. Okay, so if you observe the filter paper, so pink color patches will form. If a pink color patches, if a pink color after 24 hours at 37 degrees temperature, if pink color patches formed on the filter paper, then it indicates the presence of microorganism. That it indicates presence of microorganism. Then it indicates the presence of microorganism. So this is one technique, membrane filter technique. Okay, so these are both are qualitative methods only. This is also qualitative method, this is also qualitative method, but we want quantitative methods for in order to determine the concentration of the microorganisms. We need quantitative methods. Okay, we need the quantitative methods. So let us see what are the quantitative methods which are present. Okay, what are the quantitative methods which are present? In quantitative also there are two methods. One is E. coli test and another one is most probable number, MPN. E. coli and most probable number, both are a kind of statistical observations only. So in but MPN number, most probable number, is more realistic than E. coli index. So next is quantitative tests. So there are two types. One is E. coli index See, E. coli means it is a bacteria, Escherichia coli. Escherichia coli. So it is a bacteria which is harmless. It is a harmless bacteria. But the presence of this Escherichia bacteria indicates the presence of pathogens also. So E. coli is harmless, whereas B. coli, Bacillus coli, so that is harmful, that is pathogen. B. coli is harmful, E. coli is harmless. Okay. So but E. coli, if it is present, so then it indicates the presence of pathogenous bacteria also. And this E. coli index as well as most probable number, most probable number. So both tests are taken place in a multiple tube fermentation method. So both the test, E. coli index as well as most probable number, so both we will perform in multiple tube fermentation method. So what is meant by multiple tube fermentation method? So both these tests, E. coli index as well as most probable number, needs multiple tube fermentation method. What is meant by multiple tube fermentation method? See, we will take some amount of raw water. So from this raw water, I will be having some flasks. Okay, so from this raw water, what I will do is, I will take 10 ml of raw water here, 10 ml of raw water. Okay, 10 ml of raw water, and I will take 90 ml of distilled water. Again, in the another flask, this is flask number 1. Again, in another flask, what I will do, I will take 1 ml of raw water with, I am changing the dilutions, and 99 ml of distilled water. In another flask, what I am doing, here I am taking 0.1 ml of raw water, and I am taking 99.9 ml of fresh water or distilled water. So likewise, I am taking different dilutions, 10 ml dilution, 1 ml dilution, and 0.1 ml dilution. Again, each dilution I will take 5 tubes. Okay, we are taking 3 different dilutions, and each dilution will have 5 tubes. We'll have 5 tubes. 5 tubes of 10 ml dilution, 5 tubes of 1 ml dilution, 5 tubes of 0.1 ml dilution. This is nothing but multiple tube. For each dilution, we will be having multiple tube. Once you prepared multiple tube dilutions, after that the experiment will be taken in 3 stages. After that, the experiment is taken in 3 stages. One is presumptive, confirmative, and completed test. So once you are done with the preparation of the sample, and the next stage is identification, whether bacteria is present or not. That identification will be done in 3 stages again. So, identification of microbial activity identification of microbial activity will be done in 3 stages. In 3 stages. So first stage is presumptive. Presumptive means, so we assume that the bacteria is present. In this presumptive test, so we check whether the assumption is correct or not. So we will give some nutrient to all the tubes. So we have taken 15 number of tubes, 10 ml dilution 5, 1 ml dilution 5, 0.1 ml dilution 5. So in all these tubes, we will give the nutrients needed for the growth of the microorganisms. Okay. So we supply the nutrients at a desirable temperature for the growth of microbes for 24 hours. After 24 hours, see, whenever these microbes are consuming the food, they will evolve the gas. So because of the decomposition, I told you in the previous sessions, so CO2 is the basic gas which comes out of decomposition. That is why the alkalinity, the carbonates, bicarbonates are present in water. That is what I have told you already. So similarly here also, after 24 hours, the presence of the microorganism can be identified when the CO2 is evolved. When after 24 hours, if CO2 gas is formed and or the solution turned yellow, indicates the presence of bacteria, indicates presence of microorganism, See, after 24 hours, for 10 ml dilution, the concentration of bacteria may be more, because in 10 ml, 5 bacteria has come in 10 ml. But in 1 ml, only 2 bacteria may come. In 0.1 ml, only 1 bacteria or maybe no bacteria may come. So that is why when the dilution is less, you may not get sufficient amount of CO2 to observe. But in that cases, if you observe that the solution is turned yellow, means so there is some organic activity is taking place. Either CO2 gas you can observe, or the solution color is changed to yellow, indicates the organic activity, that means indicates the presence of microorganism. So all the tubes where you are getting this or this, yellow color or CO2, we assume that the assumption is correct. That is presumptive test. We assume that the assumption is correct. Here, whatever the nutrient we give is fit for any organism. But in the confirmative test, so we do the same test repeated manner, but only thing we change is the nutrient which is fit for E. coli. So in confirmatory test, confirmation test, we do the same thing, copy paste, but we will supply the nutrients which fit for E. coli bacteria, So in confirmatory test, we check the same CO2 present or not, yellow color is present or not, only because of E. coli. If the same thing repeated again, that means E. coli is also present. E. coli, if it is present, it indicates that along with E. coli, B. coli will present. That means along with E. coli, some kind of harmful organisms are also present. That is what is nothing but confirmatory test or confirmation test simply. Okay. So now once you done with the confirmatory, once you done with presumptive, and the last test is completed test. That is calculation of result. Completion of test. Completed test. Completed test. Next is completed test. So completed test means whatever the 2 stages we have performed, so compiling these into a form of a result. So that is nothing but the third one, completed test. So the result can be given in the form of E. coli index. Either we can give this result as E. coli index, or we can use this data to find most probable number. Most probable number. Okay. Most probable number. So what is E. coli index? First let us see what is E. coli index. E. coli index means, for example, we are having different dilutions. We are having different dilutions. So let us, I assume that we have taken 100 ml dilution, 10 ml dilution, 1 ml dilution, 0.1 ml dilution, 0.01 ml dilution, like that, and so on. Anything you can take if you can measure it. So likewise we are taking all the dilutions. So we will get a positive or negative depending upon the presence of the microorganisms. So for example, we have got positive here. That means the gas is formed. So that means positive result has come. Similarly, in 10 ml dilution also positive has come. 1 ml also positive came. And 0.1 also positive came. But 0.01 ml, no gas is formed and also no color change has been observed. That means it is a negative result. So E. coli index is defined as, so whatever the last positive result, the last positive result. So the E. coli index is equal to 1 by the last positive dilution, that is 0.1. 1 by 0.1 is the E. coli index. E. coli index is defined as, so you will take different dilutions where you are getting negative, stop there and look at the last positive dilution, and the reciprocal of the last positive dilution is nothing but E. coli index. The reciprocal of last positive dilution. Okay, last positive dilution is nothing but E. coli index, and the unit is number per 100 ml. Number, the unit here is numbers, that means these many number of organisms present per 100 ml. So this is the unit. So here for this it is 10 number of organisms per 100 ml. 10 number of organisms per 100 ml. So this is the E. coli index. This is the E. coli index. So likewise we complete the test using E. coli index method. Whereas if you are taking most probable number, whereas you are taking the most probable number, then it is different. So the results, so here in most probable number, what we do is we will prepare a table. Data of microorganisms concentration first. So if you are having a knowledge of rebound hammer, just I want to correlate it with a rebound hammer calibration. The same thing, but in a different way we are doing here. but the methodologies are same. There we are applying that method for rebound hammer. The same method we will apply here for bacteria count. See, in rebound hammer what we generally do, if you have taken a new rebound hammer, then to calibrate this rebound hammer, what generally we do? To calibrate the rebound hammer, what generally we do? So we will take a cube, okay? So in laboratory generally we calibrate this rebound hammer. So what we do is, we will take a CTM. So in this compression testing machine, what we do is, we will keep the cube inside it, okay? We will keep the cube inside it, and we will apply some nominal load in order to hold this cube. So we will apply some kind of 150 kilonewton load just to hold the cube tightly. Then the cube is tightly held in the CTM machine. Now what we will do, we will take this rebound hammer and hit it at different locations. At different 5 locations we will hit with the rebound hammer, and then we will take an average value of it, average rebound number you are getting of this cube. So now for this cube you are having a rebound number of R1, average of all these things, all the 5 readings we have taken. So all these 5 readings average is R1, okay? Similarly, you have taken, for this cube rebound number is R1, and now what I will do, I will crush this cube in the compression testing machine. I will find what is the crushing value of this cube. So I got a crushing value of F1. Similarly, I removed this grade of concrete, another grade I have inserted, and now for that let the rebound number is R2, the compressive strength is F2, so R3, F3. So likewise I will get a chart of a rebound number and compressive strength, okay? Rebound number and compressive strength. So I will get some kind of graph like this. Now if you go to site and if you hit with this rebound hammer onto a beam or a column, you will get a rebound number. So now using this chart, so if this, for this rebound number, what should be the strength? I can identify. So this is what is the chart I prepared in the lab, and using this chart, I am using this chart in the site. By knowing the rebound number, I can correlate with the compressive strength. So this is what is simple basic knowledge, because as a civil engineer we can understand it easily. The same way, in the same way, the most probable number. So these are all probabilities. This is also probable value. Okay, with this data we are correlating it. Okay, it's not an exact value, it is also the data. If how much realistic is this data, that much realistic should be this one also. Okay, so similarly what we do is, so we will take multiple tubes in the lab. And for every tube, okay, we will take different samples. Most probable number. So we will take different samples. So for example, so we have taken some kind of water. So 10 ml dilution, 1 ml dilution and 0.1 ml dilution. So we have taken 5 tubes of this. You have taken 5 tubes of this, and we have taken 5 tubes of this also. So in these 5 tubes, for some water, okay, in these 5 tubes out of 5 has given positive result. Then we record that. So here we record that number of positive results. So 5 out of 5 has given positive result. But for 1 ml dilution, no positive result has come, 0. For 0.1 ml dilution, there is no positive result, it is 0, 0. So 5, 0, 0 is one combination. 5, 0, 0 is one combination. Similarly, if it has given 5 positives and it has given 1 positive only, and it has given 0 positives, That means this is again another combination. These are all number of positive results. Number of positive results. Similarly, another combination has come. So here it has given 4 positive results. It has given 3 positive results. It has given 2 positive results. So likewise, we will be having different combinations of positives and negatives. For each positive combination, there will be some amount of organism concentration. Okay, microbial concentration. So what we will do is, for this combination, what should be the microbial concentration in numbers per 100 ml? That we will prepare in a tabular format. For example, for this concentration, it should be 5. For this concentration, it is 15. For this concentration, it is 33. So likewise, we will prepare a table chart. We will prepare a chart. This is called table dilution data. This is called table dilution data. This is called what? Table dilution data. So always the table dilution, always we keep the table dilution as 10 ml, 1 ml, 0.1 ml. Always we keep the table dilution as 10 ml, 1 ml, 0.1 ml. But the test dilution, so now if you are done with this chart, this is laboratory work. Now this chart can be used anywhere for determining the unknown waters where you want to determine the organism concentration. So now what we will do now, so we have brought this chart to the site and we want to measure the test sample. We want to test the water. Okay, so that water is called test dilution. So we have taken different samples depending upon the availability of the apparatus with you. Either you may have big apparatus, then we may take a test dilution of 100 ml, 10 ml and 1 ml. If you are not having small apparatus with you, then you will go with 100 ml, 10 ml and 1 ml. Or else if you are having small apparatus with you, you may go like 1 ml, 0.1 ml and 0.01 ml. So like that also you can go. So upon your availability of the apparatus, you can either take a test dilution equal to this or more than this or less than this. So that is where we can take anything. Okay. So but how to correlate the data? How to correlate the data? See, for example, you have taken a test sample of 1 ml, 0.1 ml, 0.01 ml. Okay. So for example, we have taken a test sample, test dilution is 1 ml, 0.1 ml and 0.01 ml. And in this dilution, we got 4 positives here, 3 positives here and 2 positives here. Okay. If you look at the table dilution, in table dilution, 4, 3, 2 of 10 ml, 1 ml, 0.1 ml, the MPN number, this is nothing but MPN. The most probable number is 33. The most probable number is 33. Then what should be the MPN number of this water? This water. See here, 1 ml we got 3 here. 1 ml we got 4 here. Now tell me where the bacteria concentration is more, where the microorganism concentration is more. In 0.1 ml we got 2 positive here. In 0.1 ml we got 3 positive here. That means here we are taking lesser quantity but we are getting more positive. Here the same, for getting the same 4, I need to take 10 times quantity. Here I have taken 1 by 10th of this quantity, 1 by 10th of this quantity, but the same number of positives. Where the microorganism concentration is more now? Here or here? Obviously here, because I have taken 1/10 of this quantity, but same number of positive results I have achieved. So that is why, so whatever be the test dilution, so the MPN number of test dilution, it is taken as MPN number of test dilution is equal to MPN number of table dilution multiplied with table dilution by test dilution. Table dilution by test. That means here MPN number of table dilution is almost 33. It's 33. What is the table dilution? Either take anything. Either if you are taking 10 ml, you take the corresponding value here 1 ml. If you are taking 1 ml, take the corresponding value 0.1 ml. If you are taking 0.1 ml, take the corresponding value 0.01 ml. So corresponding values only you need to take. Okay. So I take from table dilution I am taking 10. So from table dilution I am taking 10. So from the test dilution the corresponding value to 10 is 1 here. That is 1. So the value of microorganisms here is 330 numbers per 100 ml. 330 numbers per 100 ml. Okay. So likewise, generally we give the result of most probable number. See, the most probable number is nothing but we have to do a lot of laborious work in order to prepare the MPN chart. So once you are done with MPN chart, so for preparation of MPN chart, so we need to take different number of tubes with different positive results, and we have to check what is the microbial concentration in it. What is the MPN, most probable number, using statistical procedures. Now once you are done with this chart, now we will take some test dilution. Any test dilution you take. You can take 100 ml, you can take 1 ml, but the test dilution should be similar to that of table dilution. That means it should be 1/10 of it. 100 by 10, 10, 10 by 10, 1, like that. 1 by 10 is 0.1, 0.1 by 10 should be 0.01. That should be 1/10 of the previous value. Okay, likewise you need to take. So any test dilution you take, any test dilution you can take. So using the test dilution and from the table dilution you will get the MPN number, and if you take the ratio you will get the MPN number of the test water, raw water. So this is the method by which we can find the microorganisms concentration. Now the last one is waterborne diseases. What are the different kinds of waterborne diseases? Generally the microbial, the most probable number, there is no limit. So that should be nil. Actually it is not at all needed. In water the microorganisms content is not needed. It should be nil. But we have to reduce as much as possible. Okay. So as per IS 10500, it was given latest revision. It was given for E. coli or coliform bacteria shall not be detectable in any 100 ml sample. The limit was shall not be detectable. E. coli or total coliform bacteria shall not be detectable anywhere. Limit as per IS 10500, it shall not be detectable in 100 ml. till the distribution. So bacteria or microorganism may enter into the water at any point of time. That is why it should not be, that is why we keep residual chlorine. So because it shall not be detectable till the distribution, so that is why we have to keep some residual chlorine in order to take care of future contaminations. Okay, we will discuss that in a detailed way in treatment of water topics. Now here we will discuss some kind of waterborne diseases, and then after completion of waterborne diseases, this topic is over. Quality characteristics of a water topic is over, and we will do the numericals of this topic. Waterborne diseases. So bacteria. So we need to know what are the different diseases that bacteria will cause, virus will cause, and protozoa will cause. So bacteria generally cause typhoid, cholera, dysentery, typhoid. See, these are all waterborne. Okay, typhoid, cholera, dysentery. Okay, dysentery means motions and all. And virus through water, jaundice through water. See, virus can enter into body in many forms, but through water, if it enters, it causes jaundice, polymyelitis, and if protozoa, amoebic dysentery, amoebic dysentery, These are the different kinds of diseases that are caused by bacteria, virus, and protozoa. Okay, so there are some kind of bacteria, iron bacteria, if you know, or I don't know, but it is not harmful to human directly, but indirectly it is harmful, because iron bacteria is a bacteria which eats iron, and it causes rusting of iron. The decomposition of iron takes place in the presence of iron bacteria and oxygen. So that iron bacteria causes rusting of oxygen. When that rust enters into our body, then it is harmful. So that is, iron bacteria indirectly affects the humans. Okay, so this is all about quality characteristics of the water. So we discuss the physical, chemical, biological characteristics and its limits and method of estimation, and what are the effects of that impurities if present in excess. All those things we have discussed. We will now do the problems of all the previous GATE examination in this topic, okay, in the next session. Thank you so much.